I'm ready to go. Are you ready to go? Ready to go? Want to go? Let's go. Ready to go? Let's do this. All right, here we go. All right, let's go. All right. There we go. Okay, calculator, let's go. Pythagoras to calculator, let's go. Okay. Determinants. You know, it's a number. It's a weird number. We use it when we're working with matrices. It helps us determine some things. What those things are, I can't really tell you. But it is a number that we use as a tool to help us with where we're coming. Remember, we started at the back end of the statue, looking at it from kind of a hard Algebra 2 angle so we can come back to the front side of the statue and widen our Algebra 2 focus on something that we already know from the Algebra 1 focus. That's the idea that we're working on. And we need a determinant to be able to do that. Now, the first thing that's super important that you recognize is that this number that we're looking for, called this determinant, is only associated with square matrices. So make sure you highlight that, okay? We can have a lot of different kind of matrices and organizations of numbers, but it has to be a square matrice. Now, not just a 2x2. It could be a 3x3. It could be a 5x5. It could be a 9x9. Any square matrice will have a determinant. Now, we're not going to get into anything much bigger than a 3x3, and you'll see why when we get there, because it's a little tricky to keep track of it. But the process is the same. Once we find the 2x2 and the 3x3, you could find larger determinants if you wanted to, okay? All right, so we're going to be working with square matrices today, all right? And so the way that we notate this, we say the determinant of matrix A, and again, I'm just making up things like, hey, this is matrix A. So the determinant can be written in a couple different ways. We could say this. We could say DET, and then in parentheses, put the argument. Okay, that's the thing that we're finding the determinant of. Or another way we could do this is we could do these straight up and down bars like this. Now all of a sudden this is where it starts to get confusing because that starts to look like absolute value. But it's not absolute value because we're dealing in matrices now. So you have to keep in clear that when we write something like that, I'm not asking you for any kind of an absolute value question. I'm saying find the determinant for matrix A. That's how you read this symbolic notation. Find the determinant for matrix A. Okay, now, the determinant to a 2x2 matrix is called a second order determinant, and to find it, we're going to do a little math, and the math is going to look like this. So the determinant of matrix A is going to be element A times element D. Thank you. Oh, this is the wrong period. That's for period 7 for Luna. This is period 6 right now. So it's going to be element A times element D minus element B times element C. Now keep in mind, this is a subtraction problem, right? And if you end up with B times C as a negative number, you're going to be subtracting a negative. It becomes a positive, right? So just keep that in mind that this is a subtraction problem, kind of like our x2 minus x1 stuff that we've worked with in the past, all right? So this is our determinant. Now I'm going to use a couple of colors to highlight this, and maybe you want to have, if you have a couple colors, actually I would definitely recommend having a couple colors. If you don't have some highlighters, come grab a couple of colored pencils. Particularly you want ones that are alternating, not really close to each other in color, okay? Because it's going to be helpful for you to notate this on your paper. 2 colors. 2 colors will be good, yeah. Yeah, 2 colors. You got like orange and green, yellow and green, yellow and pink. Something that's clearly different. You can use highlighters. You can use colored pencils. I got colored pencils right up front here. All right, so here's how I'm going to do the colors, okay? I'm going to start with one color on the diagonal on my 2x2 matrix like this. And then I'm going to start the other color on my 2x2 matrix on the other diagonal like this. And I'm going to use those colors to help me know what numbers I'm multiplying in my pattern to find my determinant, okay? And I'm always going to start with my negative sloped color, and then I'm going to subtract my positive sloped color. Did that make sense? Right? This is a negative sloped line, so I'm going to start with my negative sloped color, and I'm going to subtract from that my positive sloped color. Okay, everybody good? Okay. Now, again, let's just make sure we're clear on this right here. So I want you to kind of swoop an arrow over here. So we're going to find each determinant, okay? And I just want to be clear that I could ask you by saying the words, find the determinant. That's one way I could ask you that question. I could say, another way, I could just put DET, and then in brackets, I could do something like -4, 5, 3, -10. That's another way that I could ask that question. That means find the determinant of that matrix right there. Or a third way that I could ask that question is I could go straight bar, -4, 3, 5, -10, straight bar. Notice the difference between the brackets and the straight bars, right? So when I'm using my brackets and I want to find the determinant, then I got to ask that question. Find the determinant of this matrix, which is usually encased in brackets. But if I put the straight bars around it, then you need to know that the assumption is I'm asking you, find the determinant of these values in this matrix right here. Okay? Everybody good with that? Okay, 3 different ways to ask that question. All right, so let's do this one. So we're going to start with number 1 here, and I'm going to encourage you to color and color. And then we're going to find our determinant of this matrix. And so I'm going to start with some open parentheses minus some open parentheses. And then I'm going to go my negative sloped color line. So -4 times -10 is what? Positive 40. And then I'm going to go with my positive sloped color swipe. So 5 times 3 is positive 15. And so now I have 40 minus 15, and I get 25. And so my determinant for this matrix right here is 25. Not too bad, right?
25 going straight lines.
No. Well, no. The 25 would be like, let's say we had an A out here. We named this matrix, right? So then it would be something like the determinant of A is, and then here we would have 25 like that. So that would be the answer. Okay. That's the numerical value that is the determinant that we will use. Okay. Let's try number 2. Okay. Why don't you start number 2, and then I'll kind of, lag behind you a little bit. So first thing I'm going to do is make sure I know what numbers I'm multiplying. I'm going to start with my downward sloped line and my upward sloped line. I'm going to get some parentheses going. And then I'm going to do my multiplication.
Yeah, I bet you didn't get it right. Hey, why are you screaming these things? Did you get 45? Yeah.
And you should have gotten positive 45. Right? Because minus a negative gets you a positive. Okay, you get the idea? All right, you do 3 and 4. Okay, ready to go. Come up with, for 3, -80, and for 4, -40. So, I mean, really, finding the determinant of a 2x2 square matrix is a really pretty quick and easy process, right? It shouldn't feel complicated. You should just be able to swipe, multiply, subtract. Okay? All right, so let's talk about then a third order determinant, which is a 3x3 matrix. Now, keep in mind, we did a 2x2. We multiplied 2 numbers and 2 numbers. What do you think we're going to have to do for a 3x3?
3 numbers.
We're going to have to multiply 3 numbers and 3 numbers, right? And so we could come down here to our determinant, and we'll talk about this process in just a second. But let's just say I wanted to make my first negative sloped downward swipe. Well, I'm going to start at my upper corner here, and I'm going to go swoop like that. Right? But now I got more to do here, so I got to swoop like that. But the problem is I don't have a third number, do I?
I think I know what we're going to do here. So you go -5, 5, and 2.
So what we're going to do is we're going to recopy the first 2 rows. Or columns, sorry. We're going to recopy the first 2 columns. Watch this. We're going to go like this. We're going to go 3, -5, 1. And then we're going to go -7, 4, 5.
Oh, I get it.
See what we did? And then we can do 3 swipes like that. And that's the easiest way to see what we're multiplying, because we have to remultiply all of these numbers in here. And then, of course, we can do our positive slope lines, which is going to start here, and then go here, and then go here. Now, real quick, before you start doing a bunch of math, give yourself a squiggle over here like this. Okay? So I'm going to give you a mock-up of what this problem is going to look like. Give yourself a couple of big parentheses here, because it's still going to be a subtraction problem to find this determinant. And it's going to be downward slope plus downward slope plus downward slope, and those are going to be multiplication problems. And then it's going to be minus upward slope plus upward slope plus upward slope, and those are going to be your multiplication problems. So if you want a color to match, it's yellow, 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 and then in my case, it's going to be green, 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 like that. Okay? And then let's just say this, where we've got our downward slope line where there's 1, 2, 3 values, or our upward slope line where there's 1, 2, 3 values. These are the products of the elements in the diagonal. The products, the elements, the diagonal. Okay, watch up here just real quick. Can I have everybody looking at the screen just so you can see? Watch. It's product plus product plus product. 1, 2, 3 times. 1, 2, 3 times. 1, 2, 3 times. And then it's minus product plus product plus product. 1, 2, 3 times. 1, 2, 3 times. 1, 2, 3 times. Okay? All right. See if you can find that. So your work should look like this. The first level of your work, I should see the result of the 3 multiplication problems here, and then the result of the 3 multiplication problems here, and then you can clean it up to your determinant number and then give me a final answer. And you can always fix your answer, but you should have come up with 75. How many people got 75 right? Let me see. Good. Okay. Good. Good. Nice. Nice. Good job. Good job. So what we're doing, right, is I'm multiplying this first 3 times 4 times -1. That's where this number comes from. And then -7 times -5 times 1. That's where this number comes from. And then 2 times -5 times 5. That's where this number comes from. Right? So it's swipe, swipe, swipe products, and I'm adding those together. And then it's swipe, swipe, swipe products, and I'm adding those together, and then I'm subtracting those values to get my third order determinant. What do you think? Can you do it? You can do it, right? Let's get a little practice in. All right? Let's get a few practice problems in. Okay, so let's go to the back side of that paper, and let's tackle number 6. Let's tackle number 6. So I'll just do some checkpoints along the way with you to make sure that you're tracking, but you get started on number 6, and let's see what you can do. Go for it. Okay, first checkpoint, the first thing that you should have done was that.
Affirmative.
Okay, keep going.
Affirmation.
Okay, next checkpoint, you should have given yourself a visual like that. Okay, keep going.
Are we going to have to like highlight them on?
Here's another checkpoint for you. Should have gotten here.
Sweet.
All right, and then I'll just give you the answer in the end. Okay, answer coming at you. Should have come up with 114. How many people got that right? Let me see. Oh, okay, all right.
Oh,
okay.
I did too, yeah.
Yeah, okay. Very good.
Just.
Okay, let's do one more. So this time I won't give you any checkpoints. This time you're going to do number 7 all the way through. From the top to the bottom, number 7. Go for it. Let's take a look and see how you did. You should have come up with negative 38. So check your numbers, check your your calculations up here. If you made a mistake, look up in this range here, look up in this range here. Can make some corrections and go back and then see where they came from.
I didn't start on my negatives.
But see, let me make a case here that if all you do is calculate an answer and it's wrong, I don't know what your mistake is. I mean, you could have made one little sign error here that transferred all the way through the problem. Well, that's a mistake. That's a small mistake. That's not a conceptual error. You still have the idea of what we're doing. So that's a smaller markdown than, I'm doing the wrong diagonals, or maybe I'm putting these second, something like that. So when you write your work, it helps me better know what you're doing, helps me give you a more accurate grade. Okay, good?
Yes.
All right. One of the uses, so determinants are used in a lot of different ways, but one of the ways that we can use a determinant is we can use it to find the area of a triangle on a coordinate grid. So when I think about the area of a triangle, right? Base, one half base times height, right? So if we have a horizontal line and a vertical line, it's very easy for us to calculate the area of a triangle, right? We can count this distance, multiply them and cut them in half, right? But when we take that triangle, or something like this, right? And then we rotate it and we put it on a coordinate grid somewhere, right? And maybe that's not a 90-degree angle anymore. Well, then we got all kinds of issues involved there. There's a lot of trigonometry that we would have to do in order to find the area of that triangle. Or we can take the 3 vertices that you see right here, and we can structure them in a matrix like this. And by adding a 1 column here, now think about what that's going to do, right? When we multiply across, when we multiply by 1, it's not going to change the answer at all. When we multiply across, there's that 1 in there is not going to change the answer at all. So what we're doing is we're taking something that really, this is the meat of our information right here, but that's not a square matrix. So we can't find the determinant of a non-square matrix. So what we do is we make a square matrix out of that by adding this 1 column in there that isn't going to change the values when we're doing our multiplication. See how that works? Okay. So let's find the area of this triangle right here that sits. Let's just kind of ballpark this actually. Let's sort of sketch this out over here. So let's just do a little, swoop and a little swoop, right? Okay, so P is at -5, -5, -2. I'm going to put P right here at -5, -2. Q is at +3, +9. So maybe here, like, I don't know, here-ish. So this is Q at +3, +9. And R is at +7, -4, right? So +7, so out here, and -4 is probably, what, down here-ish, like that? I'll go like this here. So R is at 7, -4, right? So let's connect these points like that. Right, now this is not a right triangle, right? So we would need a line that goes from one corner straight down to another corner at 90 degrees. Oh, what's that line called? Begins with an A. We constructed those.
Oh my gosh, I know what it is.
Yeah, you're right. It's AL.
No,
It's like a plane flying at a certain height. The altitude, right? The altitude, right? And that was where we set our compass point here, right? And then we dropped it down and we marked here, right? So that we could get our cross points because of our perpendicular bisector construction, which allows us to drop. We would have to do all of that work to find our height so that we could go base times height divided by 2. Or we can use this formula to find the area of this triangle. So let's use our determinant formula, okay? All right, so the first thing we need to do is we need to get the, see in the parentheses here, we need to get the determinant of this matrix right here. So I'll tell you what we're going to do. We're going to take our paper here. We're going to divide it a little bit here like this. And then let's write a matrix in this format using these coordinates right here. And so we'll just call P, we'll just say that x1, y1 is going to be P, and then Q will be x2, y2, and then R will be x3, y3. Okay? So we'll just go in order, make it easy. Okay, go ahead. Write the matrix. Let's see what you can do. 3 by 3 matrix.
Oh, which side is really one?
To the right. We're going to write the matrix on the right.
Oh, can I get one?
Matrix should have looked like that right there. Everybody have that matrix down? Okay. Find the determinant of that matrix right there. Go. They should have come up with this for your determinant, right? Okay. Now, it seems a little weird that you would get a negative value here, right? We're talking about the area of a triangle, right? So, yeah, right? Thanks, Jaden. Okay, so you'll notice in here that there's some straight bars, right? But you'll also notice that there's the determinant of this matrix, right? We've already asked for the determinant of the matrix by saying det parentheses x. So what we're actually saying here with these straight bars are, what's the absolute value of the determinant of the matrix of x, right? Okay, so then we could say that the area of our triangle is 1/2 times our determinant of our matrix here, right? So this is going to be negative 148. So our area is going to be 1/2 148. So our area is going to be 74 units squared. Okay, so you can see that we have questions like this one here. Wellspring is 14 miles north and 3 miles east of Chester, and so on and so forth. So here you could find the area of the landform between these three towns. You would draw a triangle. You would use your determinant matrix to set that up and figure out the area. We're not going to do that question together because we got to talk about a couple of other things before we get out of here today. All right, so let's go on to identity matrix. All right, so an identity matrix, denoted I, is again, it's a square matrix. When multiplied by any other matrix, it's going to equal that matrix. Okay, so if we had matrix A and we multiplied it by the identity matrix, we're going to get matrix A. Or if we had the identity matrix and we multiplied it by matrix A, we're going to get matrix A. So whether we multiply it on the left or the right, it's like multiplying by 1, right? Okay, so then let's talk about what I looks like for a 2 by 2 matrix. What does I look like for a 3 by 3 matrix? What do you notice? Ones and zeros, and the ones are isolated to the main diagonal that starts at the upper left corner. Okay, let's just try one for a second. Let's just actually take this matrix A right here, and let's just test it out. So let's come over here in this space, and let's go matrix A, which is -1, and then 2, and then 3, and then -5. And let's multiply that by the identity matrix for a 2 by 2. All right, now let's think about this multiplication problem, right? So this is going to be, what's the result of this going to be?
2 by 2.
It's going to be a 2 by 2, right? We know that. Okay, so then it's going to be, so this first one here is row 1, column 1, right? So then it's going to be row 1, column 1, yeah? So then it's going to be -1 times 1 is what? And 2 times 0? Okay, so then -1 plus 0 is -1. Okay, all right, now let's do row 1, column 2. So now it's going to be -1 times 0 and 2 times 1, so 2. All right, let's do 2, 1, row 2, column 1. So it's going to be 3 times 1 and -5 times 0. It's going to be 3. And then let's do row 2, column 2. It's going to be -3 times 0, or 3 times 0, and -5 times 1. That's going to result in what?
It looks similar to
Okay. -5. Okay, you see that? We got the same matrix. So when we multiply by the identity, we get the same thing. So it's like multiplying by 1. So this is your multiplying by 1 for matrices.
So when you multiply by 0, it's like the same as multiplying by 1.
Well, the combination of when one of your terms multiplies by 1 and all of your other terms are going to multiply by 0, it's going to end up being that same number, right? So in each of these cases, we were doing 2 multiplication problems, but one of them was that column times that row times that column, and then the other one was 0.
Yeah.
And so that's how it ends up being that way. Yeah. Okay, good. All right, let's talk about inverse matrices. These are your reciprocals, right? Like 2/3 and 3/2. Okay, 2/3 and 3/2. When we multiply 2/3 and 3/2, what do we get? We get 1, right? Multiply 2/3 and 3/2. That's what makes numbers reciprocals. They have a product of 1. Okay. 1 is the identity number in multiplication. What do you think is going to happen when we multiply 2 inverse matrices? No, we're not going to get a 1. We're going to get the matrices version of 1, which is what? The identity matrix.
Oh.
Okay, let's see how it works. Okay, so when 2 matrices are inverses of each other, their product, and this is really important right here, in both directions is the identity matrix. So we have to check it in both directions, okay? So if matrix A has an inverse denoted as B, then A times B should result in the identity matrix. And B times A should also result in the identity matrix. All right. Are A and B inverses of each other? Well, we can multiply them, right? Do we multiply those two?
You can.
2 by 2s, right? And we're going to have 2 by 2 results, right? Okay, so let's split up the work again so that we can make sure to get through this, right? So let's split up the work. So partner up, and we'll do a little divided down here, okay? And one of you, I want you to do AB over here. And one of you, I want you to do BA over here, okay? And let's see what you come up with for AB and BA, okay? Ready? Go. Okay, look, this is what I was just saying. Watch up here. It might be easier for you. Whoops, I wrote that backwards, didn't I? It should be BA. So it might be easier if you rewrote your matrices here so that it's very clear when you're doing rows times columns, you're not getting confused, right? Because if you do it over here, you got to be clear that it's still row 1 times column 1 like that. So if you just rewrite the matrices in the BA order, then it makes it kind of easy to go by that pattern if you're working like that. Okay, finish it up, see what you get.
Yeah, honestly, I'm kind of a little higher right now.
All right, let's take a look. Did you get it? Are these inverses?
Yes, they are.
Yeah, because you get the identity matrix both times. Okay, so let's just take a couple of real quick notes over here. All right, ready? Okay, so multiplicative inverses, otherwise known as reciprocals, work like this. 2/3 times 3/2 gives us 1, the whole number, whether you cross cancel or multiply and get 6/6. Okay? This is the one of matrices, right? We just talked about that. That identity matrix, right, is the one of matrices, right? That when we multiply by the identity matrix, we get the same thing, right? So it would stand to reason that the matrix that produces that same property of getting the same thing, like multiplying by 1, should be the result of multiplying inverses. But because of our commutative property issue, we have to make sure that we check both directions. And then when we do, we can say, yes, these are inverses of each other. Okay? All right, you get the idea? All right? Okay, one more thing to talk about. Let's talk about what happens when an inverse does not exist. Not all matrices have inverses, okay? So, if the determinant of a matrix A equals 0, then there is no inverse for that matrix. So we have a square matrix, we find its determinant. If its determinant is a real number other than 0, then yes, we can find the inverse of that determinant. Okay? So then the question is how do we find the inverse using the determinant? So let's do number 4. Okay? So first off, is number 4 a matrix that we could find an inverse for that we could multiply by to get the identity matrix? Did you just follow what I just said? Okay. Well, it's a square matrix, but not all matrices have inverses. So what we have to first do is find the determinant of this matrix right here. So what is this? We'll call this matrix A just for sake of argument. What is the determinant of matrix A? Well, I'm going to go swoop and whoop. All right, remember? We were just doing this. And I'm going to go 12 minus 6, and I'm going to get 6. It is not 0, which means that there is an inverse for this matrix. There is a matrix that we can multiply by matrix A here to get the identity matrix. And here's how we find it. Ready? Okay. We're going to find the inverse of matrix A, like inverse trig, you know, sine to the -1, cosine to the -1. Inverse trig, right? The inverse of matrix A is going to be found by doing, watch this, 1 over, so here, I'll do the generic version up here. So here's our matrix A. Here's how we find the inverse. We do 1 divided by the determinant, and then catch this. This is where it gets a little bit weird. In fact, let's highlight and highlight what happens. Element 1, 1 and element 2, 2 switch places.
What?
Element 2, 1 and element 1, 2 change signs.
What?
The opposite of. They stay in the same location, it just becomes the opposite of. Okay, here we go. What number goes here?
12. I don't know.
12. No. 6, the determinant of A.
No, 10.
Dude.
Okay. I want you to try to fill in the right numbers here. Let's see if you can do it. Here you go. You should have done that right there. Did you get it?
Yeah.
So we switched. I switched my downward sloping elements, but I kept the signs the same. And then I took the opposite of my upward sloping elements, but I kept the position the same. Now all we have to do is scale the matrix by 1/6. Okay, let's do it.
Oh.
So then the inverse matrix for matrix A at the top is what? You do it. Simplify fractions. Stay in fractions.
I thought I'd do something kooky off.
Or is it?
No, because you have to go A minus 1. Oh.
That's it.
Is it? How would you prove it?
Oh, no.
You're going to prove it right over here, right now. You're going to go A times its inverse, right? That'd be like 2/3 times 3/2, right? What should you get if you do A times its inverse?
I.
No, that I.
Yeah, but here's the thing, right? It can't just be that way. It has to be this way, too, because it's both directions.
That's a lot. Oh, shoot, I know this.
Okay, let's start with this top one here. Let's see if you can do it. Even if you get one of them done, that's a good step. Okay, let's see if you can figure out how to do A times A to the -1, or A times its inverse. Should give you the identity matrix.
I understand here. I don't know how to do it, but I know how to do it.
You'll feel good about yourself when you do this. Trust me. You'll be like, "Whoa, look what I did." Okay,
Wait, what do you mean?
here you go.
Oh, yeah.
And that'll be on the video. So, like, if you're looking at it going, I have no clue what just happened here, you can go back and look at it. But essentially what we did was we found the inverse using our inverse formula, which is right here, right? Which is right here. Pay attention to the changes that happen. So we found our inverse, and then we just multiplied our original matrix by our inverse, and we just paid attention, right? So then it was like row 1 times column 1, row 2 times column 2, whatever. You know, we were looking for that. And when we do it, and we keep track of our math, we end up here. Hang on, homework, let me give you the numbers, okay? We're not doing them all. Okay, grab the homework paper that I gave you. Right at the top, we're going to do numbers 1 through 7 all, and 10 through 12 all. So you get 8 and 9 off. Those are the long ones. Okay? All right?
Yeah, those ones are cooked anyways.
All right, I'll see you guys next week.
You better get a 5
Monday.
No.
Good job today. Don't you feel buff and strong like math buff?
I know, I'm like, yeah.